Hi, my name is Tom Zhen. I'm a solutions architect with the Amazon EMR team. Today's topic is large-scale machine learning on Amazon EMR. This is the agenda for the talk. We'll start with an introduction of Amazon EMR, followed by an overview of machine learning on EMR. We'll talk about the distributed training, distributed inference, and model serving in the context of EMR. And we'll conclude the talk with some demos and point you to some resources on how to get started with doing large-scale machine learning on EMR. Now, a quick introduction to Amazon EMR. Amazon EMR is a managed framework for running Hadoop ecosystem applications. The supported applications include Hadoop, Spark, Hive, Presto, Flink, HBase, and etc. EMR can process big data stored in S3, HDFS, DynamoDB, Redshift, or data ingested from Kinesis, Kafka, and other data sources. Common use cases for EMR include log analysis, web indexing, data transformation or ETL, machine learning, and etc. EMR is secure with support for AWS IAM roles, KMS, Key Management System, VPC, Virtual Private Cloud, and storage and transport encryption. EMR provisions and manages clusters of computers, EC2 instances, with Hadoop, Spark, Presto, Hive, Pig, Flink, MXNet, HBase, and some other distributed computing and machine learning frameworks pre-installed and configured. For applications not supported or not yet supported, such as TensorFlow, XGBoost, PyTorch, you can use the EMR Bootstrap action or the EC2 Systems Manager to install them. On EMR, you can use Jupyter Notebook, Zeppelin, and Hue as interactive user interface to run Spark, MXNet, Hive, and Pig jobs. EMR has support for the Glue data catalog for sharing data among different clusters, sharing data between applications, and for data lake support. You can use transient cluster, auto-scaling, S3, and Spark instances to cut costs. A transient cluster auto-terminates after workload is done. Auto-scaling can grow or shrink your cluster based on the metrics you specify. S3 allows you to share large amount of data, to store large amount of data at low cost. And the Spark instances allow you to save up to 90% on EC2 instance cost. Amazon EMR offers flexibility in configuring clusters based on your workload characteristics. For general purpose workload, such as batch process, you can use the M family of EC2 instance. For compute-intensive workloads, such as machine learning, you can use the C family and the P family instances. The P3 and P2 instances are GPU instances. For memory-intensive applications, such as interactive analysis using Spark SQL, you can use the R family instances. And if your application needs large on-cluster HDFS storage, you can use the I3, I2, or the D2 instances. Next, let's talk about machine learning on EMR. First, let's look at non-distributed machine learning versus distributed machine learning. Non-distributed machine learning refers to machine learning on a single machine. The pros for machine learning on a single machines are it's easy to set up and use. Most machine learning frameworks and applications run on single machines, and many frameworks are available, such as scikit-learn, NLTK, XGBoost, and more recently TensorFlow, MXNet, PyTorch, and etc. The problem with a single machine is that the size of data that can be processed is limited by what a single machine can handle. A single machine has limited CPU, GPU, memory, and disk resources. To scale machine learning on a single machine, to handle more data, or to get machine learning jobs done faster, you have to scale up vertically by using more powerful high-end machines. We used to have the Moore's law that predicted doubling the number of transistors on a chip every 2 years, but that doesn't seem to be hold anymore. So we may have reached the physical limit of silicon, and high-end machines could get very expensive. To solve the scale problem, we need to use distributed machine learning on a cluster of machines. With distributed machine learning, we can train and inference or predict on large amount of data, tens, hundreds of terabytes, and even petabytes of data. We do this by scaling out horizontally using relatively cheap commodity servers. The problem with distributed machine learning is that it's more difficult to set up and use, and not all machine learning frameworks support distributed processing. Now let's look at the different levels of the Amazon machine learning stack. At the bottom, we have the infrastructure on EC2 with the GPU and the CPU instances for compute. And we have services for managing IoT and mobile devices for collecting input data. For machine learning, we're mostly interested in the GPU instance types and the C5 CPU instance type that can accelerate machine learning workload. The P3 and P2 GPU instances come with powerful GPUs to accelerate the machine learning workload. And the C5 instance can also accelerate the machine learning workload without using GPU, but instead using Intel's math kernel library, MKL, to speed up matrix computation. At the framework level, we have the AWS Deep Learning AMIs. AMI stands for Amazon Machine Image. The AWS Deep Learning AMIs have the popular machine learning frameworks pre-installed and configured. Those frameworks include Apache MXNet, Gluon, TensorFlow, Keras, PyTorch, Caffe, CNTK, and etc. You can launch EC2 instances using the AWS Deep Learning AMI on different instance types, such as P3 and P2 GPU instances, or the C5 CPU instance. The AWS Deep Learning AMI is great for experimenting with different deep learning frameworks for research and development. At the platform service level, we have SageMaker. SageMaker is a fully managed platform that enables developers and data scientists to quickly and easily build, train, and deploy machine learning models at any scale. And we have Amazon ML, AML. It's a managed service for building machine learning models and generating predictions. And we have Amazon EMR, which we already talked about. And we have Kinesis, which is a managed platform for collecting, processing, and analyzing real-time streaming data. It can be used for collecting training data for real-time inference or prediction. We also have AWS Batch, which runs job asynchronously and automatically across one or more computers. It has also scheduling and queuing capabilities. It can be used to run machine learning related jobs. And we have ECS, which is a highly scalable, high performance container orchestration service that supports Docker containers and allows you to easily run and scale containerized applications, including machine learning applications. Some more details about SageMaker here. SageMaker comes with an easy-to-use Jupyter interface for creating, training, and deploying models. It can also be configured to connect to an EMR cluster to run Spark workloads. SageMaker supports MXNet, TensorFlow, and it has an open interface to plug in other frameworks or custom algorithm as well. SageMaker has a good selection of built-in algorithms, and the list is growing. At the application surface level, we have Amazon recognition, image and video for vision. We have Amazon Lex for speech processing for building conversational chatbots. And for language processing, we have Amazon Comprehend for text analysis, Amazon Translate for machine translation, Amazon Transcribe for speech to text, and Amazon Poly for text to speech. Those applications are API driven. They can be integrated easily with other applications. And Amazon EMR can integrate with those and other components in the Amazon machine learning stack. So those are the Amazon machine learning application services we just talked about. So when to use different machine learning tools. So SageMaker could be the first stop for your machine learning needs. It's easy to use. It has a good collection of algorithms. It scales well, and it's easy to deploy. If you find the built-in algorithm provided by Amazon AML work for you, then AML can be very easy to use, and it provides some nice features for data insights, model evaluation, and etc. And you can use Amazon EMR for large-scale distributed machine learning on big data. For vision, speech, and language processing, you can use the corresponding Amazon machine learning applications. It'd be difficult to build something better than those. And AWS Deep Learning AMIs are good for learning different frameworks for doing machine learning research and development. On EMR, 3 machine learning frameworks are available natively. So we have Amazon ML and MLlib on Spark. We also have Apache Mahout, which is the first distributed machine learning framework for Hadoop. It is not as popular as Spark ML, but it's still evolving. It now supports Spark as a backend, and it also added the GPU support. Since EMR 5.10, we added the MXNet deep learning framework as a native application. So for other machine learning frameworks not available on EMR, such as TensorFlow, PyTorch, XGBoost, and BigDL, you can use EMR Bootstrap Action or the EC2 Systems Manager to install those on EMR. And EMR supports the P3 and P2 GPU instances and the C5 CPU instances for machine learning and deep learning acceleration. Here is a select list of popular machine learning and deep learning frameworks. SparkML and MXNet are available natively on EMR. The rest can be installed using EMR Bootstrap Action or the EC2 Systems Manager. EMR can be used in every stage of the machine learning pipeline. We can use EMR for feature engineering on big data, which includes data cleansing, data transformation, and feature extraction. And we can store the feature data in the machine learning friendly format, for example, libsvm, or in query optimized formats such as Parquet or ORC. We can build models using many nodes in a EMR cluster on large amount of input data. So this is a distributed training. And we can do high throughput inference on large amount of data. So that's distributed inference. For feature engineering on EMR, we can use Spark for ETL to extract training data from raw data. Hive can also be used as well. It's slower than Spark, but it's a proven framework for processing large amount of data in HDFS and S3. We can use Presto to run ad hoc interactive SQL queries to explore data, to identify features, and to verify results. Spark is a fast query engine suitable for ad hoc queries. Now we have training data after feature engineering, but there are a ton of machine learning algorithms available. So which ones to use? Since 2012, when the deep learning model MXNet won the ImageNet large-scale visual recognition challenge, deep learning has gained tremendous momentum, growing beyond the initial image processing focus to solving wide range of problems. It outperformed the traditional machine learning algorithms in just about every field. And besides deep learning algorithms, XGBoost is the winningest algorithm in machine learning competitions. XGBoost is fast and more accurate than other traditional machine learning approaches. So deep learning plus XGBoost are must learn and can cover a good number of deep learning and machine learning use cases. SparkML has a built-in traditional machine learning algorithms for common machine learning problems such as classification, regression, clustering, and collaborative filtering for recommendation engines. So deep learning plus XGBoost plus SparkML provide even better coverage for common machine learning and deep learning use cases. To train machine learning models on large amount of data or to build large models, we need to use distributed training. There are two types of distributed training. The first one is data parallelism. Data parallelism is when the input data is too large to be processed by one machine, but the model is small enough to fit in one machine. So each machine trains the model independently using a subset of data. It could either be partitioned or by random sampling, and use the all-reduce algorithm to synchronize model parameters between training runs. Data parallelism is the most common use case. The second type is model parallelism. In this case, the model is too big to fit in one machine and has to be spread out to multiple machines. Model parallelism is less common, so we'll be focusing mostly on using data parallelism. There are a number of machine learning and deep learning frameworks that support distributed training. SparkML is a distributed machine learning framework that takes advantage of Spark's distributed compute capability natively, and it is available on EMR. So there's no additional setup needed. For TensorFlow, PyTorch, and Keras, we can use Harvard to run distributed training. Harvard is designed to run more efficient distributed training with TensorFlow, Keras, and PyTorch on GPUs. MXNet leverage a distributed key value store to hide the complexity of data synchronization. MXNet can launch distributed training jobs on a cluster using Yarn or SSH. Using Yarn is simpler because Yarn is already available on EMR. PyTorch also has a package for distributed training. XGBoost on Spark is already distributed because of Spark is distributed. So there's no actual setup for it. And BigDL is also a distributed deep learning framework on Spark. So it's distributed as well with no actual setup. Next, we talk about distributed inference. Distributed inference comes very naturally with the distributed computing frameworks like Spark and Hadoop on EMR. We can do batch inference, so that's batch prediction on big data. We can also do real-time inference on streaming data. We can use machine learning models deployed locally on a cluster, or we can access a remote API endpoint for SageMaker or for SparkML services. We can do distributed inferencing using Spark with machine learning and deep learning models. The models can be served on worker nodes. The pros on serving models on local worker nodes is that the endpoints are local and it's more efficient with no network latencies. The cons are that we need to take care of local model serving on individual worker nodes. Or we can use a remote SageMaker or Amazon ML API endpoint. The pros for using SageMaker API endpoint is that we can leverage SageMaker's model building and deployment capabilities. So no need to deploy anything on the cluster. The cons are that we have higher latency with remote API endpoint. We could easily get throttled when making large number of API calls. So depending on your use case, you can choose the one that works for you best. So model deployment options on EMR, we have those available. The MLib framework supports model serving for Spark, Scikit-learn, TensorFlow, and XGBoost. And for TensorFlow, there's a TensorFlow serving. For MXNet, we can use the MXNet model server. We can also use a Docker container to preload and run machine learning servers. And then we install the Docker container on the worker nodes. Or we can use EMR custom AMI to preload packages and use EMR bootstrap action or EC2 systems manager to start model serving on the worker nodes. Or in the simplest case, we can just load models in the Spark code. It's one-time setup per partition with map partition. It could be efficient if the data partition is large and the model is relatively small. So that's pretty much it, and it's a time for demos. And we're gonna go through the following demos. The first one is XGBoost on Spark on EMR, and the second one is distributed training with Harvard plus TensorFlow on EMR and P3 16XL GPU instances. And the last one is distributed inference with Spark structure streaming and Kinesis. So the first demo is running XGBoost on Spark on EMR. And this is the simple code. And I have some comments here to SSH to my the master instance on my EMR cluster, and then run this shell script so that I can run the following Scala code. And it's pretty simple. We first do some importing of the XGBoost packages, and then we set up some XGBoost related parameters. Number of runs, number of workers, and then we load our data, our training data and test data from S3. And then we build our data set, the training data set and tested data set using using those two data frame calls. And then we set up the XGBoost, some XGBoost parameters. And then we run this train with a data frame call to do the training. And then we do some inferencing or prediction on the test data. So now I'm gonna run this script to SSH to the EMR cluster. Okay, so this is the terminal on my Mac notebook. I'm going to SSH to the master instance on my EMR cluster. So now I'm on my EMR cluster. I'm going to run the Spark shell to run my demo script. So the Spark shell is loading, and it's going to load the XGBoost library and its dependencies as well. Okay, so now I'm going to import the XGBoost packages. And then I'm going to create the training and testing data frames. Okay. And then I'm going to build and now I'm going to build the data frame using the training and testing data. So the data, input data is in the SVM format, so I have to specify that. And you can see that the Spark is providing us feedback. Okay, so now we have both the training and testing data frame loaded. And we're gonna set up some parameters, XGBoost parameters. And next, we're going to run the XGBoost training to build the model. So since we specified 4 workers, you can see that Spark launched 4 tasks. And now the model is actually building is done. We can see how we did with the test data. So this is doing an inferencing on test data and then show the results. So on the left-hand side is the label, in the middle is the feature, and then on the right-hand side is the prediction. And then there's a probability column of the prediction. So it looks like it's doing pretty well on this data set. We do see some errors. And so that's the running demo for running XGBoost on Spark on EMR. So the next demo is running Harvard on EMR to do distributed training with TensorFlow on GPU. And we're using a EMR cluster with the P3 16XL GPU instances. So I'm going to run, so those are the things I'm going to do. First is to SSH to the master instance, and then we'll look at some of the settings, and then we'll run some training runs. So those are the training runs we could do. We probably will not run all of them because some of them will take longer, some of them take shorter, but this is the way you can test the horizontal scaling with Harvard and TensorFlow on EMR. So the first example runs just one process, one worker. The second one runs 2, and then we're doubling that until 8. On the cluster, I have a total of 40 GPUs. So now I'm going to switch to the to my console again. I'm going to SSH to my GPU cluster, the EMR GPU cluster. And so this is the cluster. Let me just show you, prove to you that indeed this is a GPU cluster with P3 16XL instances. So this is going to list the 8 GPUs. As you can see that those are the Tesla V100 GPUs, each with 16 gigabyte of memory. So this is per instance, and I have 5 instances on my cluster. So next, I'm going to just take a look at the host file, which specifies to Harvard how many sort of GPU slots, worker slots on each machine. So with 5 instances, 8 slots per instance. And then I'm going to run. The first one is just run one worker to train the model. So this is on this single machine and using 1 GPU. So it's running, and you can see that Harvard is using 1 GPU instance. So this should take maybe a minute or so. So you can see from the log that it prints the GPU memory, it prints the memory speed as well, and now it's trying to warming up the worker. And you can see that with a single GPU, we are able to process about 200 images per second. This is actually just using default settings, so it's not definitely not the best that this instance can do. All right, so this one took a minute and 12 seconds, and you can see that the throughput is 200 images per second. And the next run, we're gonna try to skip the double. We're gonna go into just maybe let's go to the 8 GPUs. So this is gonna take a single machine to run 8 tasks, training tasks. You can see that now it listed 8 devices. So it looks like we have some deprecated calls that need to be fixed. So now it's warming up 8 workers. Okay, so now it's running the training, and you can see that the throughput on a single GPU is actually lower. But then since we're running more GPUs, we're running 8 GPUs, so the aggregated throughput should be a lot higher. And the reason that it's lower is that there must be some communications and other overhead with multiple GPUs, which is normal. And by doing some tuning, you should be able to reduce that. And Harvard is designed to run more efficiently on GPUs to reduce those overhead. But I haven't done any training on those, any tunings on those. So in this case, we are getting 5 times more throughput with 8 more GPUs. So it's kind of it's pretty good, but there's definitely some overhead in there. And then so I think I'm gonna just kick off the 40 GPU ones, and we probably don't have to wait for it. Just want to prove to you that we are able to scale this training pretty easily by just specifying the number of processes we want to run. So now we're making use of all 40 GPUs. And with 40 GPUs, the overhead is going to be even higher, but the aggregated throughput is should be higher as well. So it's going to take longer to warm up the 40 GPUs. So we should see a little bit lower per instance throughput, but with all 40 running at the same time. So that's quite a bit lower. So we dropped down from 200 on a single instance to, I think, 140 on 8 to 73 on 40. So there definitely things can be done to reduce this overhead, because the cluster we set up is they're probably not located closely enough. So there definitely will be some network latencies between the GPU instances. So let's just maybe wait for it to finish to see what the aggregated throughput we get. So with 8 machines, with 8 GPUs, we got over 1,000 images per second, and we should have higher ones with 40 GPUs running at the same time. Yeah, so it's definitely worthwhile to tune the cluster, because from 200 dropping down to 70, that's quite a bit of degradation. That's quite a bit of overhead. And I think since Harvard is already trying to address this overhead issue, I think if we're using the vanilla TensorFlow parameter setup, we're going to get even worse results. Okay, so now we are getting actually pretty good at 3,000 images per second with 40 GPUs. We can definitely do better if we do some tuning, and if the P3 X10 XL instances, the 5 instances are located closer together, we should get better results. All right, so the next demo is the distributed inference demo using Spark structured streaming with Kinesis. And in this case, we're going to use the SageMaker API endpoint. So we mentioned that there's 3 different variations. And for this one, we're going to just show the using the SageMaker one. Actually, for this one, we're going to use the Kinesis comprehend because it does provide more information for sentiment analysis. So we're going to use this one to demo. But it's pretty easy to switch to different ones, which I'll show in the demonstration. And let's take a look at the code. So this is the PySpark code to run the structured streaming and to basically, in this case, we have data coming from an outside source. In this case, it's actually tweets via the Twitter API. And then the tweet gets pumped into Kinesis. Let me show that on the, so the tweets coming from the Twitter and then gets pumped into Kinesis. We have 2 paths here. One is the batch aggregate path. It basically uses a Kinesis firehose to batch up the tweets, compress them, and then store them in S3. So we get a copy of the raw data. The second path is the Kinesis stream. In this case, the tweets is passing through Kinesis and then gets processed by Spark streaming or using structured streaming. And then we inject the predictions coming from Amazon Comprehend into the tweets. And then we save the results into Parquet file, and we can save that into JSON or other format as well. And then the results can be queried using Spark SQL on EMR, using Presto on EMR, or using Amazon Athena as well. So let's take a look at the code. So this is one of the file that does the API access. So in this case, we're gonna do some the normal import for PySpark, and then we define a function to retrieve sentiment from Amazon Comprehend, and it's pretty easy. We're basically passing the Twitter text tweets, and then call the Comprehend API endpoint. It will give us the sentiment in the response body, and then we convert the textual result into the number results. So in this case, positive sentiment would be integer 1, negative would be -1, and neutral would be 0. And then this second function is using SageMaker instead as endpoint. And so it's very similar. The third one that I haven't had set up is to just call my model served locally on the worker node on EMR. So it's going to be very similar. Just basically making a REST call to localhost to retrieve the results. So going down, we are going to define a user-defined function to be used by structured streaming, because structured streaming using SQL calls. So in order to call outside API, you have to define a user-defined function. So in this case, we specify the get sentiment comprehend function. If we want to use a SageMaker or local model serving, I would use the corresponding functions. And then here we basically just do the normal setup to run Spark application. And in this case, we set up the Kinesis call. And then we create a Spark session. here, and we specify the name of the Kinesis stream from the command line, which I already set up. And in this case, we are reading in a sample tweets to, the idea is to it's kind of a shortcut. So instead of defining a complex schema for tweets, I just read a few sample tweets and then use data frames schema call to leverage a Spark data frame to automatically infer the schema. So you can definitely just define the schema by hand, which you can see it's very complex. So now we have the schema, and then we create the sentiment data frame using the Kinesis data frame. And we make some SQL calls to retrieve the results coming from Kinesis. And you can see that I'm using the schema I just created earlier in order to get the correct results. And then we added some additional columns to the original data. So one of them, so this is the most important line, is to add the sentiment column. And then the value is from this user-defined function that we just defined earlier. So basically, we're passing the text from the tweet text from the text column, and then call this UDF to get the sentiment. So this UDF basically goes out to Amazon Comprehend in this case to make the API call to get the sentiment. And then we added the partition to the data. So when we save the results back into S3, it will be partitioned by year, month, day, and hour. And then we're doing some conversions to get the hour from the data stream, And here we write out the string by the partition we just defined, and we're writing out back into S3. And this one is actually the location is here. Its location and format are defined through from the command line. And we do some checkpointing to make sure if something goes wrong, we can restart the structured Spark streaming process. And then this one basically starts the streaming process. So that's basically the streaming code. And then we have this code for pumping tweets into Kinesis. So we're using the Twippy API, Python Twippy API, and then we're basically just retrieving tweets and then pumping tweets into Kinesis. And then we have this, to run the Spark streaming, we just use this simple line to run that as a Spark submit job. We specify the number of executors, specify the executor memory, and specify the executor course, and then the Python file the PySpark file we want to run. So that's pretty much it for the setup, input, and for the input and the Spark streaming setup. And now let's look at the actual process that I have running. So this is my the master instance on my EMR cluster. And in this case, you're seeing that it's showing that I'm running the Spark streaming process here. And on this window, it's running the Twitter Twippy program to retrieve tweets from Twitter and pump the tweets into Kinesis. And I can show you just what the output looks like. This is the process that retrieves the tweets. And you can see that it's getting the tweets in real time. And then this one is the console feedback from this Spark streaming process. Okay, so now I'm going to switch to Jupyter Notebook. This Jupyter Notebook I bootstrapped onto EMR, So this first notebook, it's basically showing the program, the Python program for Spark streaming that I just showed earlier. And the second one is the most interesting one, is that now with the Spark streaming injecting tweets, injecting sentiment into tweets, and then saving the results into S3, I can query the output using Spark SQL. So now I'm using Python, using the Python 3 notebook with PySpark support already set up. And here I'm reading tweets from the output bucket for the structure streaming. And then I filter the tweets by sentiment. As you can see that this is a snapshot of the previous run that I had. In this case, the tweets with positive sentiment, I have this many. And then with negative sentiments, I have this many. And this group by query basically shows the distribution of neutral sentiment, which is 0, positive sentiments, which is 1, and negative sentiments, which is -1. The 99 are the ones that it's either caused by API error or the backend did not return a valid sentiment. And the schema that I mentioned earlier, if you want to define this by hand, this is how it looks like. So I took a shortcut to just read the sample tweets from read the sample tweets and then use data frame to infer the schema from the JSON file. And so that's the schema. It's indeed really complex. And then those are some of the queries on the tweets. So this is basically a group by query by country. So that's pretty much the demo that I have for the structured streaming with Kinesis and using a batch inferencing job, distributed inferencing job using Spark and the Amazon Comprehend API. Okay, so to get started with using Spark and EMR to do large-scale distributed machine learning, you can check out some of the resources listed here. And so that's the end of the talk. If you have any questions, we are open to answer those online.